Okay, we can start now. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Eid Mubarak for all. And today we have the second lecture for Dr. Aizzat. There are several instructions in Google Classroom. You could follow the instruction to install some software. But if you have difficulty, you can tell me and I can give you guidance how to do it. If needed, we can make a Zoom meeting and then I can get you to install the software. Okay, okay. Without further ado, please, Dr. Aizzat, we can start. Time and screen is yours.
Okay, thank you, Dr. Dimas. Okay, regarding the software, if you have a problem, you can ask Dr. Dimas or you can directly telegram me. If you don't scare, I'm not going to eat you. Okay, so the reason we are not going to do coding in the software because for practical, I need to in front of you to see whether you understand or not. But I leave the software parts as a hands-on because normally in the lecture we will go with theoretical, so that you can try to relate what is in the theoretical and during the lecture session. Okay, I'm going to share my screen now. Okay, can you guys see my screen?
Yes, Doctor.
Okay. Okay. So today I'm going to continue to a new topic. In the last lecture, we talked about what we call it introduction to the autonomous vehicle system. And when you see from the last lecture that we talk about, is there any sound from my side or what?
Yes, we can hear you.
Okay, so because I hear like a bell ringing, it's not from my laptop, right?
Oh, really? Clear, crystal clear here.
Okay. let me, sorry, because I hear some like a continuous bell.
Oh, it is because I make you a co-host. Maybe.
Yeah.
I will withdraw your co-host permission. Maybe.
Oh, okay.
You want to hear?
Oh, okay.
Okay.
Okay. So okay, no longer no sound anymore. Okay. So from the last lecture, we talk about on how we do convert from the traditional tractors into the autonomous mobile robot, or if we go straight into the autonomous vehicle development. And I think you get some idea, and then I showed to you some of the what we call it, some of the my previous case study where we convert it into from the normal golf cart and we convert it into the some autonomous system, and also we develop with the 4-in-wheel mobile robot so that it becomes the autonomous mobile robot. So for today's topic, we are going to discuss on the sensors and architectures that is required in order to convert your, for example, your tractor for agriculture into the autonomous system. So these are the common sensors that we are going to use into our autonomous robot. So when we want to convert something from a conventional non-intelligent system into an intelligent sensor, into intelligent system, we do need a sensors. So the question is, why do we need sensors in the autonomous vehicle or autonomous robot or your autonomous tractor for agriculture engineering? Is the sensor is acting like eyes for your vehicle, and each sensor has a weakness and advantages we will discuss later. Previously, when we develop a very simple system, for example, you develop your automation system, you only have 1 or 2 sensor. For example, you are develop an automation or conveyor system for your plant manufacturing system. You only have, for example, IR sensor only, right? But in order to create a dynamic system, a robot that is capable in navigating into dynamic environment, we need multiple sensors, because the reason is each sensor has a weakness and advantages. And to complement the weakness for the sensor, a sensor fusion is required and is common in autonomous system and any robotics field. So we will discuss in general what is the sensor fusion, what are the sensors required that we need to use in the autonomous system. Okay, so if you see from here, this is the common autonomous vehicle system. So if you see from the left here, this is your, we call it environment. So this is your agriculture field, for example, your paddy field. So this is your crop field. So this is what we call this environment. So if we have trees, right? If we have plants, so this is the environment. So when we are developing our autonomous system, we try to understand the environment. So how do we understand the environment is we are going to sense this environment by having a sensor. So we are going to install the sensors inside our environment. And these sensors is transmitting the data. So the data is being transmitted to our system, and this is on the most right hand side of the screen here that you can see is where we do our decision planning, whereby this is the part where you put your hardware and your software inside your hardware. So we have normally in autonomous system, we have three parts here. We have perception, we have planning, and we have control. So what is the perception? So for example, I give you one example. Perception is like we human, right? When we walk, we see through eyes and we hear through our ears, right? So when we walk, the eyes and the ears is try to get the information during walking. And this information is processed by our brain so that we know where are we, where we want to walk, and how do we walk. So the perception is trying to process multiple sensor data so that we get where is our location right now and where are we going to go without any error. So this is what we call it a perception. So in other words, the process of knowing where are we right now is called localization, and the process of knowing what is happening in our environment, we call it environmental perception. So this is the term that we use in our autonomous system. And when we understand environment, for example, this is the environment of your trees, right? When we understand our environment, we can develop what we call it our environmental models, because we try to understand our environment by having some map environment, our 3D map, our 2D map, or maybe our just the general GPS map. We call this as a environmental model, and we try to understand where is our robot's position. When we have this information, when we understand where is our robot position, then we will proceed with planning. So this is where do we plan the motion of our vehicle. So the planning is divided into three parts. We have a mission planning, we have a behavioral planning, and we also have a motion planning. So you can see that this is the part, for example, I give you, let's say you have a very big tree here in your plant field. So this is your robot here. So if I want to go at this position, I cannot cross through this tree. So my robot need to have a planning so that I need to create something like this. So during the process of navigating, not colliding with the tree, is we try to generate the path that is trying to avoid the trees so that it don't collide with our robot. So this process is, we call it a planning. So we have mission planning, behavioral planning, and a motion planning. So each of the planning category, they have different type. I'm not going to discuss in detail here. And when we finish our planning. Then we can instruct our robot by controlling the motor or the actuator inside the robot's tire. So we give the actuator command so that we try to follow this line so that our robot can go along our route. So this process is called a control process, a control system process. So like your subject, they call it a system kawalan, right? A control system. So if you see the big picture, this is the big picture of the control system. So in order to create an autonomous control system, so we need to have at least a sensor. You need to have a perception. Perception is we gather the information from our sensor. We need to plan where do we want to go. And the last part is we control it. How do we give a command to our actuator? So this control algorithm will send a command to our actuator. So our actuator is attached to our robots, for example, our tire and our steering. And when we move, then our robot will move to a new position. Then our robot will start to scan a new driving environment because your robot is already moving. And this process is being repeated. And then you send back, you do the perception, you do planning, you do control, and it keep looping until you reach your target destination. So this is a general overview of the common autonomous vehicle system. And so when we have this is the slide that you see in the current slide is the general architecture of the autonomous vehicle system. And inside this, you can see that there are on the left side, there are several sensors. For example, on the sensing part, where do we want to send our environment, we can use a camera, we can use a LiDAR, this is laser rangefinder, we can use an initial measurement unit, we can use a GPS to get the information of our environment. And then this is the computing. We use maybe one computer, two computer, or more computers, where inside our computer, we do this part, perception, planning, and control, which is our intelligent control, and the extraction. This is where you put your motors. And inside here, normally is low level, where you have your PCB board, you have a motor driver board, and here is your system. Is that your data logging, your socket, your server, your diagnosis element, the safety system. So you can see from here that the safety system, the system diagnosis will be always outside of our computing so that we can start to monitor what is happening in our system and we can do action if something wrong with our system. And in order to create autonomous mobile robot, there are two approaches. One is using commercial software and hardware, means that there are several, for example, several software ready for autonomous system, not just for vehicle. This software can be used for any autonomous application, including for agriculture navigation. And they are open source solution. So the commercial solution is we need to pay because the toolbox is there and we need to just using a toolbox without doing much of the algorithm. And the second approach will be using an open source. Open source software, you need to code a bit, you need to understand the coding a bit, but the advantage of the open source software is all the code there is free and you can use the code development for your own application. And in fact, you can do a commercialization. You can sell your product using an open source software. So on the slide here, you can see some of the company, they are trying to sell it, the commercial software. And we are going to talk about the sensor and how do we use the sensor in our autonomous system. So we are going to talk about LiDAR later, camera, initial measurement unit, what is the principle of the sensor, the odometer, the GPS, the LiDAR, and the last thing is radar. And of course, there will be more sensor used, but these are the most common and mostly used in when we want to convert our system into an autonomous vehicle system. And the first part is the LiDAR sensor. So if you see from here, this is the LiDAR sensor. So You can see that this is the LiDAR sensor that we use in our lab. This is a 3D LiDAR. So you can see it's quite not too big and not too small, but you can see that there is like a mirror here, but inside a mirror there is a laser inside here, and we will have one cable here. So this cable is connected to this machine, and normally via Ethernet, via LAN cable, and we transmit the data for data processing or data transmission. So LiDAR has two types of LiDAR. We call it a 2D LiDAR or 3D LiDAR, where the purpose of this LiDAR is to scan the environment and do the maps. And we want to create the map of our environment. So the term of the LiDAR is originated from light and radar. That's why we call it LiDAR. The LiDAR is commonly used to make a high resolution map. This application is surveying, geoinformatics, geography. You can see that laser guidance, and this is the real purpose of the LiDAR before we have the autonomous system. So normally they use it in the surveying, in the, for example, in the agriculture to scan the topography of the area. And because of the ability of the LiDAR to detect the topography of the area, so we utilize this technology so that this technology is used in our control system and navigation for the autonomous vehicle. And this is the concept of the LiDAR. So if you can see from here on the picture that I shared to you in the previous slide, you can see that there is a mirror covering here. This is what happening inside the mirror. So for example, LiDAR, they have several types. For example, I can say we have a 1-channel LiDAR or 60-channel LiDAR, or we have 32-channel LiDAR. So it depends on our LiDAR model. So for example, when I say that the LiDAR is 1-channel LiDAR, so you can imagine inside your LiDAR, they have one motor here, and on the mirror here is like a laser here, whereby the laser will be transmitting a beam here, and they have a transmitter and receiver inside the sensor. So for example, if you see on here, this is my sensor here. I want to scan this, we call it this object. So what happening when I give a laser beam? So the LiDAR will be scanning something like this. This is where my sensor will be do the scanning. And when they do the scanning, the reflected light will give us information. There are two information that we will receive from this LiDAR. The first information is we will receive the distance from our transmission from object, and the second is what is the angle that we get. Means that we will receive where is our angle and where is the distance. For example, in this part, I will receive the angle and the distance. So each point, I will receive the angle and the distance. So what happens when this LiDAR rotates? We will be able to know at each iteration, at each rotation, we'll be able to know or to plot the angle and the distance data like you see in the slide just now. So with that, we can estimate that, okay, for example, for this case, you can estimate, okay, this is the box. We are inside a box or square shape, and we have one cylinder in 2D format. So for example, in this example of motion, we only have one channel. But if we add more like this, for example, right now we only use one, but if we add more like this in different angular, for example, I add another motor with light laser inside here, then we can scan in the 3D format, so that we can get the information of a 3D object. So this is the concept of the LiDAR. So we use, in summary, we use the concept of the light transmission, and we have a motor, and it rotates and give the timing, and then it calculate the timing reflected, so that you get the object information. So we have two types of LiDAR. 2D LiDAR. For example, this is Hokuyo brand from Japan. So the 2D LiDAR is you only get the information of the 2D plane, like in the previous video example. Or another example is we have a 3D LiDAR. So the 3D LiDAR is consists of multiple channel. So normally when we buy the 3D LiDAR, they have a 60 channel, 32-bit channel, or 64-bit channel, and the highest one is 128-bit channel. So you can see that the higher number of channel that we have, the more information that we can obtain from our sensor, the more precise 3D image that we can create when we do a scanning. And this is, for example, Velodyne, the most famous one in the autonomous system development. This is a company from the US where they have a 3D LiDAR. And when we have a 3D LiDAR, because of the 3D LiDAR, we can convert it into the 2D LiDAR reading. So let me show you one of the example inside my laboratory. For example, we developed one of the 3D LiDAR application. So you can see that the 3D LiDAR is at here, and we put it into one small box. And our purpose is try to use this 3D LiDAR and try to generate it into the 2D format. So you can see from the video here, when we work this LiDAR, we can generate. We can see here on the map on the gray color, whenever the person is walking, they can start to scan the environment and try to generate. So we use our algorithm and we try to generate a map from this environment. So we need to walk. So this is good. For example, if you see here, we are doing the map inside a building. This is inside our laboratory. When we do this scanning inside laboratory, we can generate the map inside our building, because we know that inside a building, we cannot use a GPS sensor, right, to generate maps of our building. So this is an advantage whereby you don't have to do an actual measurement in order to generate a map. What we do is we just walk in the green color, green trajectory. You can see from here in the green trajectory here. We just walk just a short distance and you generate a complete map already. So this is the advantage if we have LiDAR. That's why the LiDAR is being used a lot in the autonomous system. And this is the how we read the LiDAR. So normally the LiDAR format, they have normally we call it a point cloud format. So this is the LiDAR data type, and this point cloud format will have this information inside our system. So they have X, Y, and Z point here. So and also the range, means that the distance from the base or from the origin of the LiDAR. And some LiDAR, they have another information, which is intensity. So intensity is trying to measure the light, the type of the object that you are trying to reflect. So if the object is in very bright in color, they have a very high intensity. Some of the LiDAR, they don't have this information. So when we have X, Y, Z and range, we can plot it into this what we call it the LiDAR point cloud. So you can see that it consists of the point X, Y, Z, and also the range from the origin. And from this point, for example, we have something like this. We have something like this that we read in our LiDAR. So we can reconstruct it using some algorithm, using some math. We can find our neighboring and we try to create line from our point here. Like we do regression, right? You try to create some equation like equation. For example, the trees here, So we can create something like this and we cluster it into, we say that, okay, this is one layer or this is one object. So when we do like this, then we can reconstruct our 3D map into some object, something that we want to classify, or some object recognition using the LiDAR processing or image processing technique. So this is what we do when we get the raw data. So on the left side is a raw data. So it's the information that we get from the sensor, and the right side is the process data. So this is what we get. And when we have LiDAR, we also have a camera. So the camera is one of the sensors that is mostly used in our autonomous vehicle system. Why? Because the camera is very cheap, right? For example, you can see that the first version of Tesla vehicle, the commercial autonomous vehicle in the US, in the first version, they don't use LiDAR at all. They only use what we call it a camera and GPS. So means that they save cost a lot because the LiDAR is very expensive. And the camera, you can get a very cheap camera from less than $100, right? You can get a very good, and then you can do image processing for object recognition. So the concept of the camera is, we call it a digital camera, use an array of millions of tiny light cavities or photosid to record an image. So this is, we have the image sensor. We get the light source here coming to our camera, and the camera is trying to trap the image, and this image data is being logged into the digital circuit. So, and we have normally RGB layer, red, green, and cyan layer, and we will do the image processing. So using a camera, we can do a machine learning technique, artificial intelligence technique, to recognize the object. And for example, if we train our image data, we can use it to track the motion, for example, the human motion. So when we are able to do this kind of thing, we are able to track the image that we can do the control system. For example, if we track the human using a camera sensor, you can stop your vehicle by giving the actuator or the throttle command to give a 0 value so that you can stop your robot. So this is the example of the camera sensor. And also, in using a camera, this is what is widely used in the world right now. So image classification. So using camera, for example, for your case for agriculture, you can detect, for example, the plant or the trees, the fruit maturity. So using image processing, when your vehicle approaching the image, the fruit, you can recognize the fruit, and you can instruct whether your vehicle want to go or pick up that fruit or not using the image classification. So this is using a machine learning technique. So if you understand Python, so in Python also we have a machine learning toolbox like TensorFlow, Anaconda also you can install using a TensorFlow. And this technique is very useful if you want to develop an intelligent application of the robot that you want. So this is, for example, in this slide here, you can see that we can train our image to recognize the car, or we can train our image to recognize the type of lane. For example, the crops lane that you want to recognize, and you think that you can move your vehicle over there. And this is the example how do we read and process the image camera. So normally we will do the processing in pixel. So the pixel are represented into a metric form for each frame, and each dot will be represented with a numbers, and the numbers will represent the color. For example, this is the image that we capture from our camera. And you see here, there is a white color over here, and there is a black color over here. So when we represent it into our camera metric, the white color is represented by a 0, and the black and gray color will be represented by certain number. So when we do, the way image see, the way we see the image is like this, and the way the computer see the image is by having the camera metric, so in number. So when we understand this number, actually we can do the image processing, manipulating this number to get some feature extraction that we are interested inside this number. So this is example. If we overlay the image that we get with a number in the metric, so this is what we get inside. And after that, when we have a camera, then you will have the, we call it the IMU sensor. The IMU stands for initial measurement unit. So the initial measurement unit is try to calculate the rate of change of your vehicle. So for example, this is your mobile robot. So normally in mobile robot, we try to move in front, right? We try to move in front, and that's why you can see that most of the sensor, the LiDAR, the camera will be put in front of the vehicle, because when you have a sensor in front of the vehicle, that you can do a scanning in a very good field of view. However, when we want to have, or we want to predict the motion, we want to know how much our vehicle rotate. For example, if I am giving some steering value of my tire here, I want to know what will be the rotation per second. For example, in 1 degree, in 1 second, how many degree my vehicle rotates. For example, in 1 second, maybe my vehicle is rotating for 1 degree. So I can predict in 3 seconds where will be the heading of my vehicle. So this rate of the orientation, we call it is rate of change tracking. So means that you can measure the rate of change in 3 axes, X, Y, Z. And when we have this rate of change, we can fuse it with our other sensor to detect the overall movement of our vehicle itself. So this is the example if we have the IMU sensor exist. So if you see here, if we install, for example, if we install the IMU sensor, so you can see that this is your Z-axis. So normally our Z-axis, we try to measure the yaw axis, and on the X-axis, we can measure a roll axis. You can see that it rotates left and right. And on the Y-axis, you can measure the pitch axis of your system. So normally, when we put our robot here, normally the Z-axis is pointing outward from the screen, and this is your X-axis, and this is your Y-axis, and your Z-axis is pointing outward from the screen. So this is how do we put the sensor placement in our robotic system. And this is, you can see here that how do we put the IMU sensor. So normally the IMU sensor, we will put maybe in the middle of the our vehicle, or in the middle between the 2 rotating tire. So for example, you have a left and right tire, you have your drive here. So normally sometimes we will put it IMU sensor at this location, or you can put it IMU sensor at this location. So when we put the location of the IMU sensor is very important, because there will be a calculation based on where do we put it, so that we can calculate what is happening to the rate of change at different position. There are calculation over there. Okay, but normally we will put it at the center. And when we put IMU, we can use it for tracking a motion detection, so that when we put, you can track, for example, using a drone motion, so you can have some prediction of the motion involved inside your system. And the next sensor is odometer. So the odometer sensor is like IMU, we call it an inertial navigation sensor. It's used to track the trajectory and the distance travel of the vehicle. So Like the autonomous vehicle, we have IMU at the center. So this is the rate of change of the orientation is measured by the IMU. When you have a rate of change, means that our robot can be detected whether you turn right or you turn left. But normally the IMU is not precise if you want to track for a longer distance of our motion. So that's why whenever we have a tire here, we will install a tire with odometer. So we will install the odometer inside here. So whenever our tire rotates, you can predict the translational motion. So when we combine between the translational motion and the orientation motion, and you can generate or you can predict where is your vehicle is moving. So that's why we call it the sensor fusion is very important in the autonomous mobile robot. That's why we use a lot of sensor in order to get where is our vehicle is moving. And when we combine between this one, we can fuse with other sensor to create the motion here. So for example, you can see the black line here is the reference. The reference is that we want to follow this line. So we want to follow this line. But this is our robot. So when we use the IMU and odometer, we can plot the red color one. This red color can be plotted using the IMU and odometer so that you know that, okay, we want to go to the red line, but our line is currently on the red color. Sorry, we want to go to the black line, but our current line is on the red. And we can calculate what is the error between the red line and the black line. And if we have a good tracking, if you can see on the here, you can see that the red color line and the black color line is very small. So what can we say for this one is the smaller the deviation between the black and red color line, the higher accuracy of our robot to follow our trajectory. So that is why we need the trajectory information of our vehicle so that we can compare where do we want to go. If we have the smaller error here, means that we are on a good track so that you can go, your vehicle is currently following the track that you want your robot to go. So this is important because we want to make sure that we are following our path. And the next one is the GPS sensor. So this is GPS sensor, global positioning sensor. So this is to get a global localization sensor. So if you see from the previous slide, in order to get the position of X and Y position in our coordinate, we fuse between IMU plus odometer. We fuse between the IMU plus odometer to get the XY coordinate of our robot. For GPS, if you don't fuse with any IMU odometer, you still be able to get the X and Y coordinate. You still be able to get the X and Y coordinate. So this is why we call the GPS as a global localization sensor. So the advantage of the GPS sensor is the GPS does not have biasing error. We will discuss later what is the biasing error compared to the initial measurement unit. So this sensor have some noise. We will see what is the noise later. GPS, they don't have this noise. And however, the GPS is very sensitive to the environment because the way the GPS communicate is via the satellite triangulation to get the location of X and Y. And if the triangulation is not accurate, for example, when during that measurement at certain location, you don't have a good satellite number, so the triangulation is not accurate. So we will have very less error, very less accuracy of our sensor. And in fact, if we have a building, we know that the GPS low frequency is not good at passing through the building walls or trees, or in a place where we have a lot of trees or tunnel. That's why you can see that when you are using GPS for navigation inside a tunnel, you will have a GPS signal loss. This is some of the GPS errors. However, compared to the IMU and odometer sensor, when we want to get the X and Y position, the advantage of IMU and odometer is we don't have this kind of errors inside a building. So that's why you can see outside in open space, GPS is very good sensor, but for a very crowded with streets and building, we cannot rely 100% on GPS. We have to rely on other sensor. That's why multiple sensor is required inside our advanced system so that we generate a robust tracking of our robot. And a normal GPS, normally normal GPS, they have about 2 or 3 meter error. So means that if this is my vehicle location, my GPS reading is within this error. So within this region. So that maybe my sensor will read the position at here, or maybe at here, or maybe at here, or maybe at here. So in autonomous system, 2 or 3 meter errors are not acceptable, especially in the localization, because we need a centimeter accuracy. For example, because for example, I give you example on the road. When you are driving your car is deviated by 3 meters. So you are on different lane already. Maybe you are on the right lane, which is not a correct lane. So that's why we need the accuracy of our GPS to be as small as possible. So the RTK GPS is often used for more. RTK stands for real-time kinematic GPS. Is often used for more accurate positioning for civilian GPS. So by using the RTK, we can achieve 1 to 5 centimeter accuracy, but the disadvantage is we need a reference base station for that. So what is happening is we have a satellite over here. This satellite will transmit to 2 parts here. So the first part is to your GPS inside your robot, inside your tractor, for example, and another one inside your base station. The base station here is a non-position, is that we already know our non-position coordinate of X and Y at the base station. And when we get the coordinate here from the satellite, you will get the X satellite coordinate and Y satellite coordinate. So theoretically, the X satellite and Y satellite coordinate should be the same number. But because of the error of the environment, of the satellite, of the building, the cloudy weather, you won't get the same number. You will get the different number. So if we calculate the difference between these two numbers, we will get the error, right? So the error that we get is the error that is currently happening at the measurement time. And if we have a car here, whereby a car is also measuring the GPS data at the same time, when we receive the data from the satellite, we assume that we have a location data of X and Y plus error. You know that the data has error, but we don't know what is the value of the error. So what happened with the RTK GPS is it tries to calculate the error by having minus it with a non-position. So we send this error to our robot. So when we know the error, if we minus this error, you'll get the actual location of your vehicle with no errors. So that's why we can reduce the accuracy of our GPS from meter accuracy into centimeter accuracy, because using the RTK GPS algorithm, we can eliminate this kind of the transmission error from the satellite. So for certain application, for certain non-environment in certain place, we can use RTK GPS because our robot is navigating during the area only. But If you want to cover your robot in a very dynamic location, in very random location, we cannot rely on RTK GPS. So there are pros and cons and depending on your applications. And the next sensor is the radar sensor, whereby this radar sensor, we will use it for obstacle or movement detection. So normally we will, radar sensor is very fast sensor. It keep do the scanning, and the radar sensor is categorized based on the frequency. So we have high frequency radar and low frequency radar, and each frequency we will put the radar inside our vehicle and put it at certain angle so that it used to detect the blind spot, the object passing through, so that we can do appropriate control system for our system. And this is the latest technology. We call it a LiDAR sensor. So this LiDAR sensor is like a LiDAR, but it is more low cost compared to LiDAR. LiDAR is much more expensive, and they have a good range. And also some of the LiDAR, they don't use motorized, like a rotating laser range, so that you have a more robust control or more robust sensing for your sensor. So this is the some of the autonomous vehicle technology with LiDAR. They still use the same laser transmission, so but with a small form factor, and they can do a scanning. So normally we will use a LiDAR for scanning the in a very short distance. Okay, so right now we have been through with what we call it, a basic on the sensors that is being used a lot in environment. So next is we try to understand what is a sensor fusion in the autonomous system. So when you see the sensor overview that I share with you guys, we can see that each sensor has their own weakness and their own strength. For example, the encoder to read the speed of a robot and the steering angle of the robot is a high speed reading sensor where we have a precise measurement. However, the bad thing about the sensor is we will have a displacement error due to biasing error during sensor integration with noise. The GPS is catering this kind of error with no biasing at all, which is very good one. However, the GPS will fail when we have a surrounding with building, trees, and also the reading rate if you want a faster reading. LiDAR is high measurement rate and precise. We can get a 3D data. However, the bad thing is you introduce a higher processing power and complex algorithm. Camera is a good sensor, low cost. We can use a multiple application for machine learning. But the bad thing is the camera is only good for a good image environment, especially at a higher light. But if you have a very bad weather, a very rainy weather, or during at night, the image quality may be distorted for low light condition or harsh weather environment. This is the bad thing about camera. And for IMU, initial measurement, we have a high speed reading, a precise measurement, and however, the IMU also have a biasing error, seems like encoder, odometer, because these two type of sensor, we call it an initial base sensor. So the initial base sensor, they are very prone to the biasing error. So by having the knowledge or the fundamental understanding about the good and bad things about your sensor, you can determine or you can judge based on your application. For example, your agriculture application, what is your cost, your maximum cost you are willing to spend? So if you know your maximum cost you are willing to spend, then you can select the appropriate sensor. And when are you going to spend it? Where are you going to spend it? For example, you're just going to spend it during the daytime only. So maybe you just need a camera and several sensors only. Or we only need in a small scale only. So we don't need to use GPS. We rely on our encoder is also enough. So it depends on your application. So, and then the application will determine how you configure the architecture of your autonomous system. So next, I'm going to introduce a basic overview of the sensor fusion in the autonomous system. So what is sensor fusion? So for example, this is your robot, right? So when we want to track our robot, this is actually your actual robot location, right? This is the location of our robot that we see from our eyes. But when we send it via sensor, we don't really get this location. We get another location. So the difference between the location that we get from our sensor between our robot, we can say that we have error over here, right? The error, sometimes when we get a raw data from our sensor, is very high. That's why we need to fuse the sensor using another information from other sensor to verify where is the actual location of our sensor so that we can do a correction. So the process of using multiple sensor is called a sensor fusion, whereby the objective is trying to achieve a corrected measurement. So this is our initial sensor that we measured. This is our actual robot location. And this is the actual location after we do a sensor fusion technique. And we can see that although there will be error, but the error is reduced and as close as possible to the actual robot's location. So this is the purpose of why we want to use a sensor fusion for our robot. And for example, if we read the encoder speed, right? So normally we get a theta dot. Theta dot is our encoder speed. When we want to get how long our robot has traveled, the displacement data, we can do the integration. So you do the integration in your programming where you get the total displacement and plus noise. So this is the error, right? If we repeat the same looping every time we do the integration to get the displacement data, you can see that the noise will keep adding. We keep adding noise every iteration. So you can see that the value of noise here will become larger. So this noise is we call a biasing error. So if we plot it over time, you will have your noise will be raised exponentially. So that's why encoder, odometer, or IMU, if we try to measure it, for example, if our robot is trying to navigate in a perfect circle, but when we measure by sensor, you don't get a perfect circle, you get something like this because of the noise from your sensor reading. So we want to correct this noise by using a sensor fusion. Okay, so I try to show you the example of in my lab, how do we do sensor fusion. So this is an example, we use this robot, a small mobile robot, whereby this robot consists of the odometer. We have an encoder or odometer sensor on the left and right side of the tire. And we don't use camera, so we use ultrasonic sensor. Ultrasonic sensor over here, you can see that we have ultrasonic reading over here. So we use two sensor. So if you see here, the odometer is initial base sensor, means that they have a biasing error, and ultrasonic sensor is non-initial base sensor. We use it to get like a radar sensor to get a distance. So the way we do sensor fusion is we try to find a landmark so that when we get a landmark, we will provide a correction to our odometer reading. So in this stage, we use one technique called a Kalman filter. They call it a Kalman filter technique. It's an algorithm implementation on the sensor fusion, where I don't want to go in detail here, but I just give you guys overview. They have two stages here, predict and update, whereby the predict state is we use a kinematic of the robot to predict the state estimate from our robot. We try to predict it, where will be the next state, and the update it. So the update it, we try to compare what we predict and what we measure from sensor. So using this error, we try to do a correction of our robot's location. So there will be equation, but I don't want to cover it because it is quite detailed here. But this is how we do it. We have two phases alternate: predict, update, predict, update, predict, update, until you get a very precise measurement of your localization of the sensor data. So the localization is the ability for us to locate our object. So we do or we measure the environmental information to obtain the location information. So for example, in this case, you can see the triangular in the black color here is the triangular in our experiment. And the red color here is the one that is measured by our sensor. And actually our robot is navigate at a perfect triangle here. But when you get the reading, you still get the error here from your robot odometer. And how we do it is, you can see on the right camera here, we move our robot at a perfect manually. We move at a perfect triangular. And you can see the green color here is the like a black is our landmark. So we use this landmark to measure our what we call it, our distance from the landmark using ultrasonic sensor. And we try to compare what happened if we don't do a sensor fusion, what is the error, and what happened if we have a sensor fusion. So this is the example. So if you can see here, this is the data that we get if we don't consider a sensor fusion. You can see that the green color is the robot. You can see we have the red color here is the robot's trajectory. But if we use a sensor fusion, you can see that the deviation between the black square is reduced compared to the first one. Although we still have this one, but in overall you can see here the deviation here is being reduced. So this is the camera view that we have for our robot. So this is the example of the sensor fusion example for our robot. So any question before we proceed to the next topic?
Is there any question? You can ask directly. I see no question in chat.
Okay, no question in chat.
One question from chat.
Okay.
From Andika Ananda, I'd like to ask something about the LiDAR itself. How could it read back and receive the data from the laser that is being transmitted? Does it has the same system that is being used in a sonar or way different? Time of flight, maybe about time of flight.
Yeah. Okay, let me open this slide first. Thank you for the question. Oh, is the name I forgot already?
Andika Nanda.
Okay, Andika. Thank you for the question. So the principle of LiDAR is we use a light reflection, whereby in the sonar you use ultrasonic reflection. So in sonar you use a wave transmission. So from the waves we transmit the wave and we reflect back the wave, right? But for the LiDAR we use one single light source, and this single light is being reflected back by having what we call it a photosensor. So one is using light, one is using wave. There are two different working principles. Okay, so that's why using a LiDAR you can achieve a point-based accuracy. Means that because every light you have a very precise point-based accuracy compared to the sonar. Sonar is like you have a wave whereby they have a general estimate based on where is the distance compared to the LiDAR. Because LiDAR you can have every degree of angle you can have every point compared to the sonar. So this is the difference between the LiDAR and the sonar. I hope that I answer your question.
Okay, thank you Andika Nanda for the question, and Dr. Aizzat. Okay.
Okay.
Okay. Yes. Okay. Is there any question? Other question? You can ask directly. If there's no question, I want to ask some question
Okay,
actually.
Dr. Dimas, no problem.
For the LiDAR time response, it is quite fast because it
Very,
needs
yeah.
rotation. But
Yes, it's very fast.
oh, very fast. Okay.
Okay, I give you one example from, later we show you the video of our LiDAR, but the LiDAR, okay, it will rotate 360 degree. So if we have, for example, 60 channel, you have like 60 micromotor that will be rotating at 360 degree for, there we have a sampling time, but what I can say is how fast is LiDAR for one rotation, right? For 360 degree rotation, one complete rotation, I can get about 300,000 points. 300,000 points. Yeah, that's why the size of the LiDAR is very big. So you imagine for what is, it's not 1 second, it's one sampling time. For example, the sampling time of the LiDAR is 0.01 seconds. So 0.01 second, you get 300,000 coordinates, and you imagine in 1 second, you imagine how many sampling you have.
So many data.
Yeah, so many data. So we did some measurement. For example, we did record some, for example, in 5 minutes, right? In 5-minute navigation, when we record our data to play back, we have like 30 gig of data just for LiDAR only, not adding another kind of sensor. That's why it introduced the complexity and the processing time of our system. So this is the thing that we have to consider when we want to use a LiDAR. Okay.
One more question,
Okay.
Doctor.
Okay.
Previously, you show us how LiDAR can map the room or your laboratory room, and how the LiDAR, how the sensor could get the position of itself. Does it have IMU or GPS?
Okay, good question actually, Dr. Dimas. Okay, there are two kind of LiDAR here. One LiDAR is some are very cheap LiDAR. They only come with a standalone LiDAR, right? So when we have a standalone LiDAR, so for example, the way we measure, right, like in this slide, right, you can see that we have, for example, this is the map that we generate. So let's say our robot move, we will have the deviation. For example, you can see that the square shape is being moved to other coordinate, right? So we use the difference between these two maps. For example, like image processing, you have two different frame, right? So we use the difference between two different frames, and we try to calculate what is the orientation change and the displacement change. So from that, you can generate the what we call it the displacement, and then we can we can combine this data into one single map. This is one thing. Or if you have budget, you can buy or you can fuse it the LiDAR with IMU. So if we fuse it like LiDAR with IMU, we can get a more precise data. So in this case, you can generate a very good map. Like in the video that I show about the mapping, I don't use IMU. I just use one single LiDAR only. But one single LiDAR only, we can get map data, provided that you don't have a very fast in the orientation change of the LiDAR. You cannot rotate your LiDAR very fast. Otherwise, you will have error in the mapping environment. But if we use IMU, we can rotate very fast, and we will still have a good mapping.
I see. Thank you very much, Doctor. I hope that we are here can purchase LiDAR soon, so we can try by ourselves.
Yeah. You can try it first.
Thank you.
Okay. So maybe I will share some case study after the sensor. How do we use it? Our sensor. Okay, in this case study, I'm trying to share in the previous lecture that you see that we developed what we call it the sensor from golf cart, right? And then until we develop using our actual car, for example, using a proton car. In this slide, I'm going to share. This is my current research development in UMP. we try to develop another project which is called Smart Campus Autonomous Vehicle, or the short name is SCAF. In my lab, we call it Autonomous Vehicle Laboratory Lab. In this slide, I'm going to share some of the sensor that we use and some of development phase that we experience. Maybe not everything is sweet, right? We have some failure also. So we are going to share this one. So maybe from your side, Dr. Dimas, you can utilize our experience and share with your students so that we can have a good collaboration maybe in the future. So this is the slide that we are going to share on how do we start. On the back here, you can see that this is our lab, Autonomous Vehicle Laboratory Lab, and this is our shuttle bus that we try to develop autonomous vehicle experience. Okay, just some very quick. We have some of the researcher that inside this field. Previous researcher also they involved in Japan with R&D. They call it a Liman's car. Like I don't know about this car, but it's an electric car. We have inside our two researchers from Japan that is focusing on the dynamic of the vehicle itself. So they are focusing on the dynamic of the vehicle. Like me, I'm focusing more on the algorithm development of the vehicle. So the way why I'm trying to tell you guys this about when we want to develop this kind of project, we need to have a good composition of team, because when we have a very large project, it's not just one single field. So we will have multiple fields. Maybe we need some expert in mechanical, we need some expert in programming, we need some expert in image processing. But everyone need to understand the general architecture, like I showed in the first slide, the general architecture of the autonomous system, so that everyone understand this general architecture and everyone understand their own rules when we want to do the sensor integration. So this is some history on how do we start. When we want to start this bus development, we start with small thing first. So this is what my previous researcher, Dr. Hewan from Japan, he did develop like mine also, some golf cart. So the golf cart also we install it with some, for example, here you can see some odometer here and some sensor electric vehicle. And also we did a lot with benchmarking. We go to some industry. So this one is, I went it myself to the autonomous vehicle test track of Volvo at Sweden. They call it Asta Zero. So this is the first autonomous vehicle testing track in the world. So whereby they have a lot of, for example, here you can see there is a dummy building here. This is autonomous truck being passed through here to see the junction. This is the autonomous Volvo here in the development. I did test. I did become a passenger to test some of the latest technology. It's very good experience. And they have a junction. They have some dummy kind of thing to check on the intelligent monitoring system. And we go to Sweden, for example, for benchmarking. Some of the this autonomous platform is being developed by a French company. So they deploy it for awareness at the Sweden's campus, Chalmers University. So it's like a very compact shuttle. So you can go inside the shuttle, and there will be one AV engineer inside here just to set up the systems. Then you can try it for free for navigation around the campus. So you can see that there will be what we call it, nice experience where you see how the autonomous vehicle work. And we can see that they are more advanced because, yeah, of course, they have a plenty of budget. When we want to develop this kind of project, it involves a lot of money. So if we have a lot of money, I think we can do the same. They are being sponsored a lot by a very big automotive company like a Volvo, Volkswagen in Europe. So that's why they have a lot of funding lah. I'm quite impressed when I went there compared to our country. We have a very limited budget. Okay. Okay. So we present some of our paper. And inside, I would like to share with you a experience with one of my PhD friends. We are still collaborating with him right now. He went to Sweden. He get the opportunity to work in one of the Sweden's companies, Sensible Oil. So he is one of the principal researcher that is responsible to develop this kind of algorithm for the autonomous vehicle. But you can see they have a very sleek profile here, very sleek manufacturing. Of course, again, because of the budget. And yeah, it's very good to know that we have representative from ASEAN country that is involving for this very big project. And yeah, we have collaborated to produce some of the books, paper is for the autonomous vehicle field. And in 2015, where is me and my friends start with the AV development. Of course, we start with a small platform first. So that's why if you see in my previous sharing, I also during it at the previous PhD level, I also start with RCCA. So RCCA or drone is a good platform for students to start because it's not that expensive. I think your university can fund. We use a very just a very cheap hobby like Arduino, Arduino Pilot, some IMU sensor, very cheap non-industrial sensor, just to show the concept. But although we are using a very cheap one, we using a very good technique, for example, differential technique, we still can achieve a very good accuracy. So if we have a small budget, it does not limit. We cannot say that we cannot start. So at least start something that is within our budget rather than we start nothing. And so this is our start. We start with this sensor development. What we do is we have a GPS sensor only, and we use some open source software, and we apply it with our algorithm for using differential GPS technique. So you can see that we can go autonomously in an open area. We can go to the point number 3 until we go to the point number 6 from our home position autonomously. So as I said, GPS, if we have in a very open area, we can achieve autonomous system without using many sensors. So for agriculture, right, maybe you have an open field, so you don't need to use LiDAR sensor, expensive sensor. Maybe you just use one single GPS sensor with IMU is enough. Just for example, for using a drone or using a rover to monitor the crops, kind of thing, if you don't need a precise information. So from this video that I want to emphasize is using GPS alone, we can achieve an autonomous motion of the system.
I'm sorry, Doctor.
Okay.
How much you spend for this project?
You mean the cost?
Yes.
The cost for the the cost. This one, the RCCA. I tried to give in RM. I don't know how to convert it. Okay,
yes,
the
RM is okay.
RM is okay. Okay. The RCCA, I use a Ford RCCA. It's a brand one. You can get a cheaper one. I think it's about 2,000 ringgit. I think for the cheap one, similar like this, because this is the original Ford one, maybe you can get less than this, maybe less than 1,000 ringgit for the chassis of the RCCA. This is the Arduino Pilot, is about RM 400 ringgit, if I'm not mistaken. It's about something like that. So this is the GPS is let me recall back. It's 100 something. It's about I don't remember the exact amount. Maybe it's 100, 200 something. And this Arduino Pilot already come with IMU and Arduino installed here. And we modified. We use our own RC remote control, because the default remote control you cannot program it. The default remote control. So we use if you see from the slide here, we use our remote control here. This is a bit expensive, about 1,000 ringgit Malaysia. 1,000 ringgit Malaysia, because we would like to program it. If you don't want to use it, you can program it using a keyboard only. For example, you program it using a keyboard. then you can create an autonomous system. But I don't want to bring along my laptop everywhere, so I just buy this one so that we can program it. So you can see that 1,000, 2,000, it's about 3,000 ringgit you can achieve one autonomous GPS system, right? So
I hope maybe we
it,
can do it here to start with the autonomous research.
And in fact, this tire also is suitable for outdoor. This is crawler. We call it a crawler RC car. So the crawler also is suitable for outdoor because they can navigate in a different terrain environment. So and in fact, if you see the YouTube video, they use this RC car to navigate in a high inclination uneven terrain. So they have a very high torque motor. So that's why we use this crawler for testing. So in fact, you can put a very cheap low cost, or you can just use Raspberry Pi if you want to do some image processing. This is just an example where if you want to start cheap.
Yeah. Thank you.
Okay. And then we developed some electric wheelchair. We have an in-wheel motor over here. We modify and we put some battery and some processing controller inside a wheelchair. And this wheelchair is able to have what we call it. For example, if we navigate in a different slope, right? For example, you have in high slope area. Normally in Malaysia, the slope for Okrio for the wheelchair person is not standard. Some of them are very high inclination. So what this wheelchair is able to do, we can adjust the torque and to make sure that it does not fall down. So it can auto brake itself if it's too fast. So this is like our charity project. So we deploy it in one of the mosques inside UMP for this project. So like the charity project for our university. And after that, we developed our first compact electric vehicle. So you can see that this is just a prototype for research only. That's why it's in no chassis here. No casing here. So we have two in-wheel motor over here, and we have a rotary encoder, two rotary encoder over here, and here you will have we put a battery. So but you don't see the battery here. And here you have a motor driver regulator, and we still have a manual control over here. But when we press the electric by-wire throttle here, we need to program our controller here to control these two independent motors so that it achieves the same performance as a normal car. So because we are converting from the normal conventional car into the electric motor kind of thing. So we developed this for our research, and we publish some paper. We have some mathematical modeling where we verify it, and we also have developed a test car inside our university, whereby this is using a Proton Persona platform, where we put some sensor inside here. We have some instrumentation, but the difference is we don't put motor at the actuator to control it. This is more on the data logger only. So we use this is to measure, to estimate, and to see the dynamic characteristic of our vehicle. And this is also a cheap cost if you want to develop yourself. We try to compare with our industry, the AGV platform. In the industry, is very expensive. I tried to ask from one of the company called ClearPass Robotics, the Jackal. There is a very famous platform. They call it a Jackal robot. It's very expensive. The cost is about 100,000 ringgit, including sensors, some API. So what we did, because of it's too expensive, we developed it ourselves. The chassis cost is only about 5,000 ringgit only with the board inside. And we have our laptop, and we use LiDAR is about 20K. So the most expensive one is only LiDAR here. It's about 20K. So about 30K you get one small outdoor AGV, about 30K. Compared to the, if we want to buy the commercial one, is about 100K. So it is a 70K difference. So we save a lot of money. So that's why we try to develop our own outdoor mobile robot. Yeah, budget limited. We don't get much grant actually. Okay, so this is one of the benchmarking visit. Previously, we went to Sweden, and then this one we went to Korea. So if you can see the yellow color, is one of the autonomous unmanned vehicle developed in Korea by Prof. Hyung Myung. So this is one of our like our partner, where we always invite this professor for our conference to give the talk. They have a very advanced technology for autonomous vehicle. Yeah, of course, a very good funding also. And if you see on the left, in this is the robot that is being used in Korea. They buy a Jekyll, the one I talked about just now. It's very expensive platform, but actually the Jekyll is using an open source software as well. Maybe I will share in my slot, the last slot, what is the software being used, so that you have some general software overview, what will be using in the autonomous vehicle platform. They also have a LiDAR, but the LiDAR is have some inclination to scan this area, but mine is more on the scanning on the horizontal area. Actually, we use a Jekyll with the same size as our benchmark. That's why you can see that it's quite similar. So we try to develop our own platform. And this is some sharing on the Sweden, where they have a very complete solution at their campus. And the landscape, they already imply the EV architecture compared to our country, because yeah, our country, we rely a lot on the petroleum, right? Because our profit come from, for example, in Malaysia, you know, Petronas, like you, Dr. Dima also study in the Petronas, right? So we rely a lot on from the normal gasoline fuel. So that's why you can see that we have a very less electric infrastructure in Malaysia. So, but in Europe, they already matured. That's why when the EV is already almost everywhere, that's why they are very good. They accelerate to go to the autonomous system. So you can see inside the university also, you can see that there is a logo of the industry is being supported by the very big company in the university itself. So with that, they have not the funding from the government, but also the funding from the industry as well. The industry, in fact, when we went to our conference in Sweden, the major sponsor is Volvo. They sponsor it. And yeah, in our ASEAN region, our participation in the autonomous vehicle is very small. So for example, in this Europe, we can see that, yeah, only me presenting from Malaysia. So I hope that Dr. Dimas can venture in Indonesia, so that we can create
Indonesian there.
yeah, so that we can collaborate on creating our in ASEAN region conference for this topic. So yeah, we are very small. This is the truth that we as ASEAN, we have to collaborate more in order to expedite our technology. This is the thing of the sensor that is being used. For example, they use a 2D LiDAR here. They use a 2D LiDAR. So you can see that they have a map already. So the autonomous vehicle is only be able to navigate inside the campus only, because they already map inside the campus. But if we want to navigate outside the campus, they cannot, because it is not programmed to work outside of the environment that they have been programmed. And yeah, just a short one. If not finished, I will continue in the last slot. Where do we start is we try to develop talent development. This is the most important part. So the students need to be equipped with correct fundamental knowledge, right? So because we as lecturer, we don't have much time, right? We only have a very limited time to do. We are involved with a lot of things. We involve in management things. So when we equip our students with a correct knowledge, they can work if they are very passionate about this one, they can work from morning until night in the laboratory just to do some project that they are very passionate. So what we do is we teach them some fundamental software, how to use the software, how to integrate, and we teach them on how to do simulation. That's why in the hands-on, I give you some simulation tools to get familiar so that you can do some movements. For example, like here, we try to simulate what is happening in our roads. We use the simulation, and after that, we try to program the shuttle. So before, you can see on the back here, this is when we start with a frame development of our autonomous shuttle. When we start with this one, the frame will take some time to fabricate. Of course, you will have a lot of error. So when we develop our simulation environment, we can do estimation, the simulation, we can simulate the measurement of our sensors. And this is some of the training we did. Okay, and here you can see that when we develop it, yeah, of course, we spend a lot of time to develop the frame for our the first autonomous shuttle. And on the right side here, this is when we try to do some testing on our first platform delivery. There is a lot of things that we learn when we want to develop one system from zero. Myself is not expert in mechanical design, but there's a lot of mechanical design involved when we are developing this frame. So that's why when we develop the system, we need people from different expertise so that we develop a very good complex system. And if you see from this slide, I don't know whether you recognize this on the this guy. Maybe Dr. Dimas recognize the this is our our ex-prime minister. So our ex-prime minister, he was very interested. I don't know how he get the information on our project. He came to our laboratory and see ourselves multiple times about during the frame fabrication. In fact, this is not yet completed yet. So, and yeah, we don't announce it immediately because we would like to keep it in a low profile. But he came in without any official invitation just to see some of the development, and we are explaining the concept that we want to achieve during the fabrication development. And this is some of the our student where we demo project. You can see we install the LiDAR at the top location here. And next, we do every research. We have every simulator. We have a SLAM whereby we use a mapping, a LiDAR mapping. We have traffic sign classification and drive-by-wire inside this location. So here you can see that we develop our own simulator. So before we test on the actual system, we try to install our algorithm inside our simulator. So we have one steering using a gaming steering, and we put it into our simulator. So this is our simulator. So, and then we load the actual environment, and we use a steering like a gaming simulator that you can see from here. So using the gaming simulator and our simulator, we can install the sensor. So we can install the sensor and we can load the environment. For example, you want how many people inside your building. And when we load, you can see that there is a car in front of the vehicle, and we can start to read the sensor reading. We can start the motion. So when we start the motion, we can do the image processing. We can do the scanning. So this scanning is going through our computer, and we log the data. And after we log our data, we can do offline processing. For example, we can do LiDAR image processing kind of thing. We can use machine learning. So we record the data. So you can see from here, and we use, yeah, this is like a real environment. So yeah, this is testing inside our laboratory. And we have traffic sign classification. using an image camera. We install the image camera inside our vehicle, and we can see that whenever there is traffic sign, we try to train the data. And they can recognize is there any warning sign, or is there any, for example, some signs, so that this information is crucial, for example, at the intersection, because when we have this image, we know that what will the vehicle will be able to do. We need to stop it. For example, in your agriculture field, right, you need to put some signs so that your vehicle be able to know, okay, this is the checkpoint that I have to stop, right? For example, this is the speed limit. So if the vehicle is getting the speed limit, so it will slow down our autonomous vehicle. So this is how we put it using a camera, and we do some offline processing, and we train using the machine learning technique. And yeah, maybe this is the last part before I continue it with the next session. And then we do it, the lane tracking inside our campus to detect the border. This is just using image only. We don't use a LiDAR yet. I will show you in the next session how we use LiDAR. But here we can detect the curve. For example, in the agriculture, you want to detect the border of your field, right? So we can use the image processing technique. So we eliminate the complexity of the LiDAR and reduce the cost. So I think I will stop here. Actually, I have more things to share to you guys, maybe in the next session, in the detail of the project development. So because the time is running out, maybe I pass back to Dr. Dimas.
Yes, Dr. Aizzat, thank you very much. I could see a lot of work that you have been you had done. And it is very interesting for us to learn from you. Okay, is there any question from the audience, from the students, or any of the lecturer that join this session? Any question? Don't be shy.
Thank you. Okay, no problem. Welcome.
From Mujarah Khotimah, maybe you could ask directly.
Yeah, you can talk in Malay, in Indonesia if you want.
Okay, it is quite a long question, so
okay.
So
the question, I can read it myself.
Okay.
Kalman filter, depend prediction model and error in colors the deviation. My question, we like to share what is the important thing to make a model prediction, especially technique how to do it. Okay, so when we have a Kalman filter, so normally the Kalman filter depending on our model prediction. So if you see here, I will cover in the next slot about the kinematics model of our Kalman filter and the state space model. So normally when we develop a motion model for our vehicle motion, normally we will use these two things. Either you use a kinematic model to predict the motion of your vehicle, or you use a state space model. So normally the Kalman filter will be using a linear model, which is the state space model, to estimate the movement of the our model. That's why in order to predict a good accuracy of our filter, that's why if you can see in my slide previously, when we have our test car, we will try to do a lot of data logging in order to get a correct parameter data of the vehicle itself. So when you have a correct parameter data, for example, if I give 20 degree steering angle, I will get 0.01 yaw rate, right? So this is the model that I already evaluate from my manual measurement. So if I have this kind of information, so I can get a parameter of the vehicle. So this parameter can be used in the Kalman filter, so that it will generate what we call it correct prediction of our system. And sometimes we don't rely on just two sensors only. For example, in the video that I showed to you guys, I use ultrasonic sensor and odometer sensor. But sometimes we use more than that. We use GPS, we use IMU, and we use odometer, and we fuse with LiDAR. So I have a video to show that we use multiple sensor, but in the next slot, this thing we have a more accurate reading compared to only rely on 2 sensor measurement only. I think that, hope definitely that answer your question. You are mute, Dr. Dimas.
Okay, thank you very much, Dr. Aizzat.
Okay. Okay.
Is it all right, Mujaro? I think all right.
Okay.
Is there any other question before we end this second session of 3-in-1 program for Dr. Aizzat? No question.
Okay, I will be uploading a code because some of you already installed the software. I will be uploading a code after this session so that you can try some simulation and try to understand it first.
Okay, just for note for the students who have difficulty in installing the software, then you can make appointment with me to guide you to install the software and introduce the software. But the appointment is please make it for each class, not one person.
Too many students.
Too many students. Yeah.
Okay.
Okay, so for each class. Okay. And then just one announcement for the student of the Agricultural Engineering and Biosystem Study Program. Now currently our faculty of agricultural technology open a project about autonomous tractor, so you can apply to be the assistant researcher for that project. Please fill the form and we will select based from your information. Before we end the session, there is one more question from. Yes, you can ask directly, Muhammad Hadi Kurnia.
No problem.
Okay, thank you for the time for asking my question. I want to ask in the explanation before, Mr. Aizzat explained that the autonomous vehicle needs to be programmed within the campus area only because of the mapping is only on the campus area. But is there any way to develop a system that we can place it outside the campus area, but no mapping required? I mean, like the vehicle can map the map itself by itself. Is my question clear?
Okay, yeah, I understand your question. Okay, the one, thank you, Mr. Hadi Kurnia, for the very good question. So if, for example, if we want to do it outside, for example, outside, what is our plan? For example, outside in the road that we don't program it, we can do it like using a non-mapping technique, like you are using a camera, right? Using a camera for lane keeping, we call it for lane keeping. When the vehicle is able to navigate autonomously using a lane keeping, what we can do during this navigation is we try to collect the LiDAR or the mapping data. So what we will do is during the first navigation, your vehicle may be able to navigate autonomously, but with a less intelligent, because we don't have any information on the road first. So you imagine that you are a new person coming to a new campus, you don't have information on the map, right? So you just try and error. But after a second or third try on the same area outside of the campus, this vehicle is start to get intelligent because you already have some map data. You can use this information of data to improve your location or your tracking control of your system. So what I want to say is, whatever the system, if we first let it navigate in unknown environment, it is not really intelligent yet. It needs to learn. It need to learn, it need to do its own mapping for several times, and then it become intelligent. That's why because of this thing, that's why you can see that most of the manufacturer, when they deploy the autonomous vehicle, they don't what we call it, they don't simply put in the unknown environment, because they are dealing with the safety factor, right, with the insurance. So that's why they are playing safe, they put in the known environment. But if you want to suddenly put in the unknown environment, this is the step. You put it first, let it learn, and put it several times, and then it become intelligent, something like that. But of course, it involves a lot of process, a lot of factors, and a lot of knowledge as well.
Okay, thank you very much, Dr. Aizzat. Now
Okay, no problem.
time is up for us. Now already 10. I think Dr. Aizzat also very busy.
Okay, no problem.
Okay. Thank you very much for all today. For Dr. Aizzat, there's also some lecturer here, Professor Sumardi, Dr. Bagus, Mr. Darmanto, Mr. Ubaidillah, and all of the students. Thank you very much for joining us. We will see you again next week on the last session for Dr. Aizzat lecture.
Okay.
So we have very limited.
Yeah, very limited.
Lecture. So hopefully next time we will invite you again.
Okay, no problem.
Yes, so we will see you all again next week on the same time, Monday, from 8:20.
Okay.
Please keep check your Google Classroom for any update, and for any problem you can contact me or chat in Telegram with Dr. Aizzat.
Yeah.
Thank you very much. See you again. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you everyone. Thank you. Selamat Hari Raya.
Thank you very much. Selamat Hari Raya.
Okay, bye bye.
Bye bye, Dr. Aizzat.
Okay.
Thank you, Dr. Aizzat.
No problem.